Here's a mathematical model for the population of flies. So let xn denote the number of flies after n days or on day n. And then we also will assume the xn is between 0 and 1. So here 1 does not mean one fly. It means the maximum amount, the maximum population of flies. So 1/2 will be half of that population. And let h denote a constant between 0 and 4. And we will explain, what is 4, where does this 4 come from. And you can think of h as some kind of growth rate, but it's not strictly a growth rate. We don't really care what it means right now. So the mathematical model would be the following. So initially, you assume the population is x0. It is between 0 and 1. And then on day 1, the population is calculated as h times x0 times 1 minus x0. And then on day 2, you take the population of day 1 and apply the same formula, you get day 2. And on day 3, you apply, you take the population of day 2 and apply the same formula. So in general, we let fx be hx, h times x times 1 minus x. And then, if the population on day n is xn, the next day the population is calculated as f of xn. So this is the mathematical model of the population of flies. So you start with the number x0, and then you apply this f again and again. Each day you apply the function f. What fx look like? So fx is a parabola. So it has a 0 when x is equal to 0 and when x is equal to 1. It is 0. And the maximum value is achieved when x is 1/2 in the middle. And this maximum value would be h over 4. So remember that this system is, the population is evolving in the way of applying f again and again. So in order to do that, we need the f map 0, 1 interval to itself. Remember, we assumed the population is always between 0 and 1. So when we apply f to this population, we apply it again and again. It shouldn't jump out of 0 and 1. So this means the maximum value h over 4 is between 0 and 4. Between 0 and 1, and h will be between 0 and 4. So that's why we assume h is between 0 and 4. So the thing that we want to show you in this video is the following graph. So we want to plot the population in this graph. So the horizontal axis will be the timeline, so day n will be n, and the vertical axis will be the population. So the height represents the population of the flies. And we want to show you what this graph look like. This graph depends on the initial population x0 and on the growth rate h, but h is the most important thing. So you will see, if we care about the population, what happens to the population, what is the population eventually when n goes to infinity, you will see that the x0 doesn't matter that much. It's this h decide what happens eventually for the population. Okay, now let's plot the population of each day in this coordinate. So the vertical axis is the population from 0 to 1, and the horizontal axis is the timeline. So this is on day 500, this is on day 1000. So we have a lot of points here. So the initial, like h, we start at 0, and then the initial population is 0.3. And what I will do next is press this button, to increase the h. When I press this button, h increase 0.1. When I press this button, the h increase 0.01. Okay, now let's increase h and let's see what the graph look like. Okay, now h reaches 4, it cannot go any further. So let's see this process again. This time we maybe with less point. Okay, let's see this process one more time. So when h is less than 1, the population dies off. But if h is greater than 1, the population decreases, but still it reaches to a limit. Okay, when h reaches 3, one line split into two lines. When h is greater than 3, the two lines separate. Two lines splits into 4 lines. Four lines split into 8 lines. And we are in chaos now. Among chaos, sometimes we still have those straight lines. Okay, let's see this process one last time, and this time with less point. So let's change the initial value, it doesn't matter that much. Okay, now I will increase h. 1h approach 3, one line split into two lines. And here we want to look into those two lines. So notice that so the point goes like this: up, down, up, down, up, down, up, down, up, down. So that is the point on the upper lines correspond to even days, and the points in the lower lines correspond to odd days. So as a sequence of numbers, the population as a sequence of numbers does not converge anymore, but the subsequence converges. That is, if you start with the population x0 and then you look at the population 2 days later, and then 2 days later, 2 days later, 2 days later, 2 days later, it converges. And similarly, if you look at the population on day 1 and then look at the population 2 days later, 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 it converges. And we will see that as h increases, those two lines becomes 4 lines. So let me decrease h a little bit. So maybe here, you start with the population and you wait 1, 2, 3, 4 days later. It kind of look at the population 4 days later, 4 days later, 4 days later, it will converges to a number. We keep increasing h. Now we are in the status of the chaos. Let's summarize what we saw here. So when h is between 0 and 1, we see the population of flies goes to 0. And this actually can be see very easily from the relationship between the population of previous day and the next day. So we know from the relationship, we know that next day the population is less than h times the population of previous day. If h is less than 1, and then each next day is a fraction of the population of previous day, eventually you will die off. And when h is between 1 and 3, the population of the flies goes to 1 minus 1 over h. So how do we get this number 1 minus 1 over h? So first, we saw that when h is between 1 and 3, the population goes to a limit. So this is the relationship between the populations in one day and the next day. And if the population goes to a limit, let's say if it is a, then on the right side in the xn also goes to a. So we have this equation, and then we can calculate that a is equal to 0 or 1 minus 1 over h. And from the graph, we know the limit is not 0, so it is 1 minus 1 over h. Of course, when h is equal to 1, it is still 0. So for the case when h is greater than 3 and less or equal to 3.570, so this number, I copied from the book, some book. It is not clear. It is not that clear when I did the demo, but this is the number. So when h is between 3 and 3.57, you see the population, even when n is very large, you see 2 lines. Sometimes you see like 4 lines. You will see 8 lines. You have, if you have like a better, graphic, computer, you can see 8 lines and 16 lines, things like that. So this corresponds to, the even sequences, goes to a limit, and the odd sequences goes to a limit. Here, it corresponds to, a subsequence that goes to a limit. And how do we calculate, this limit? Well, again, you start with, a relationship, function like this, and then you say, okay, if a sequence, goes to 0, if the subsequence goes to a number a, not 0, and then you have this equation. The sequence goes to a, x to n also goes to a, and then you solve this equation. It's a polynomial equation. And when h is greater than 3.57 and less or equal to 4, all I can say is it is chaos. That's all the cases. So the point here is that, with this one example of the population of flies, we think it as a dynamic system, the population changing, and we see different cases. Sometimes we see the population stabilize to a number. Sometimes stabilize between 2 numbers, or 4 numbers, and sometimes the population is just a complete chaos. And this one example with these cases, they actually represents the flavor, the cases that you will see in other examples in other dynamic systems.